Hello, everyone. Welcome to the seminar. AI is the hot topic nowadays. In the recent years, we have witnessed so many breakthroughs in many fields like speech recognition, image recognition, and the language generative models. So behind those breakthroughs are the new advanced learning technologies. Today, I'm gonna introduce one of such interesting learning technologies. It is called contrastive learning, which doesn't receive sufficient attention. And constructive learning by itself is not very powerful. It cannot change the game, but if it is combined with other learning technology, it can certainly greatly improve the performance. So first of all, if you have some experience with image classification, you already know that most of the convolutional neural networks have similar structures. Basically they have many multiple convolutional layers stacked together, and sometimes those convolutional layers intermix with some other layers like activation, polling, batch normalization, and dropout. Those are just optionals. But basically, if you think the input data, get transformed along the pipeline, and if you think in such a way, the input feature are transformed from the early stage, like very low level, very local features, as it passes along, the pipeline, it becomes more high level and more global and more abstract. So you can think that way. At the end of the convolutional, blocks, you actually have some kind of features. You can view those convolutional layers as the feature extraction. So at the end of the pipeline, you can attach a fully connected layer to classify something you want to classify. So, like, either a dog, a cat, or something else. So this is the typical structure. And let's take a look of ResNet 50, which is a very popular one. It's usually trained with the ImageNet. And you can see that in the first block, we have 3 convolutional layers grouped together as a combo. And there's a skip connection, which is the unique feature of a residual neural network, which is used to mitigate the so-called vanish gradient problem. So we repeat those combos 3 times. You see here, 3 times. You have 1, 2, 3. And then the next block actually, follows the same philosophy, but with different kernel size, and or channel numbers or whatever. So the next time you repeat this 4 times, and also the next block we repeat this combo six times. Lastly, you can see at the end of the convolutional layers, we use a global average pooling, which, to get a vector of size of 2048. So we pass a vector of such a length into a fully connected layer to generate the 1000 classifications, because ResNet 50 is used to classify ImageNet, which has 1000 classes. And so this is the structure. So what can we better improve the structure? So if we cut the, the head of the network, which means I cut off the fully connected layer, and we take the base part as a feature extractor or feature encoder, then we can do something differently. So basically, today's task is to train the ResNet 50 model to classify Sci-Fi 10 datasets. The difference is that the ImageNet, the size of images in the ImageNet is 224 by 224, but here Sci-Fi 10 is much smaller, it's 32 by 32, but still it's a color image. That's why we have the channel 3 representing red, green, and blue. And the example is from the official website of Keras. And in this example, we're gonna make a comparison study. So we are gonna train, the neural network in the traditional way, and secondly, we're gonna use our, contrastive training to see what improvement we can get. Okay. So here we are, like we showed before. We are gonna to do some surgery in the last part, in this part. So basically, we are gonna, cut off here and remove the old original fully convolution layer. Instead, we are gonna add a drop out the dense layer, drop out and dense layer. So basically, first of all, I want to point out that dense layer is the same as a fully connected layer, okay? And the dropout is optional. The two dropout layers are used to, to overcome the overfitting problem. And why we use two dense layers instead of one? That's because the output from the global pooling here is 2048, output neurons, and we want to get an output of 10 because we Sci-Fi 10 has 10 classes. So from 2000 to 10, we want some middle ground. So we want first to reduce some 2000 to a few hundred, from a few hundred to 10. So that will give us a better accuracy. So that's the typical, strategy. So what is constructive learning? So let's go back. So here we can see that one way is we train this neural network as a new, as a new one after we do the surgery, remove something, add something. But another way we think of it is, how about we train the base model separately in a way we can, to let it generate a better features here to feed to the classifier layers. So that means we want to train it in two phases. The first, we train the base model. Second, we train the added layers. So that's the idea. But what's the goal to train the base model? We are gonna we want its output to maximize the difference between sample of different classes and minimize the difference of the sample from the same class. So that's the purpose. After we train that, then we were gonna, add a new layer to the base model. And when we train the added layer, we freeze the base model. So that's how we do it. Okay. So here is the first step. So we cut it, we add a dense layer. So that's the first step. We're gonna try to make sure it come out, the feature comes here, has the feature like minimize and maximize something. And once we have this base model trained, we're gonna remove this dense layer and replace with this structure, drop out. So that's the ultimate goal, the final neural network. Okay, so these two phases that we want to train. So another question we're gonna answer is how to measure the similarity between two feature vectors. And the simplest way is use dot product. But here before we do the dot product of two vectors, we actually first normalize each of them before we do the dot product. So that gives us the cosine of the angle between the two vectors. So the meaning, probably most of you already understand the mathematical meaning of why we use this one as similarity measures. Thinking about a 2D cases, suppose we have animals of like different groups like cow and sheep or some other animals. If the horizontal axis represent weight, the vertical axis represent height, and you can see the same animal maybe have a small groups. At least the example that I gave probably not so obvious. If you compare a cow with a rabbit, you can see there are a great difference. So the same group may be similar, so their angle are quite close. So the theta very small, and the cosine 0 gives the highest number. But if the cosine theta is 90-degree difference, that means they are quite irrelevant. And if they are 100 degree, they are completely the opposite. So that's why the dot product is a good measurement of the similarity between two feature vectors. All right, so we are gonna use a TensorFlow add-on package, because it has a very convenient method to measure the loss function. It's called the n-pairs loss. Basically, you need to supply two arguments. The first argument is the label. The second is the prediction of the model. And because we train the model with mini batches, so for each batch, so the y, the ground truth, is a vector of batch size. And the second one is very interesting, is a matrix, is a so-called similarity matrix. So each element represents the similarity between sample I and sample J, okay? And so how to calculate the prediction, convert the prediction into the matrix. So basically, once we have a vector for each one, because this vector is our feature vector, we need to convert it to a matrix. So the way we do it is we use the matrix multiplication, but the second one we just do do a transpose. So that's the simple way to do it. And once we have this calculated, we got the similarity matrix. We are ready to use this loss function. And inside this loss function, how it works is not our business anymore, but it's the responsibility of this function. But here I just want to illustrate how it works. So basically, suppose if you have labels like this, the diagonal you remap it to the same shape as the prediction. You see the diagonal outrules because it's self to self, but here we have two same class, one twice. You see true here and another true here. So that's how we remapping a label vector into matrix. Once we have this ready, and it used cross entropy the same way as before, and the last one is use the mean of all. So that's how it works. All right, so I think now we have sufficient knowledge to to go to the code. So here we are. Let's see the code we have. So like I said earlier, this code is from the official website. This is the author and some comments and introduction. So also he mentioned that we need to install TensorFlow add-ons. So I already did that. So the first part of the code is import some modules like TensorFlow, TFA, NumPy, Keras, and also because we use Keras layers a lot, we just import it, okay? But you can also use this one. Without this one, you can use from here, you can use tf.keras.layers is the same thing, but this more convenient, okay? So first, let's prepare the data. We first define the size and the number of classes of the data, and then we use this convenient function to load the data. The Sci-Fi 10 dataset contains, I think, 50,000 training samples and 10,000 test samples. Although you think, okay, this is quite big, but it's actually not. The reason is, 50,000, we have 10 classes. So each class has 5,000 samples. Consider it's a dog is one of the class. You can see, does the 500 samples really cover the the variety of dogs, because we have so many different breeds, and for each breed we have either young dog or a small puppy and adult dogs, and also each dog have different pose and different colors and different lighting conditions. So there's a lot of variation there. 5,000 images may not be sufficient to cover so much varieties. So what we need to do is we need to do data augmentation to increase the variety of our data set. So here you see, is first do the data normalization. I will explain this later, but the data augmentation section is this part. First, we random, flip the images, and secondly, we randomly rotate it a little bit. The angle is quite random, and we stretch the horizontal and vertically a little bit randomly. And now I'm gonna talk the first one in these structures in this block. And this normalization is gonna use the mean and variance. Basically, for each channel of our image, we're gonna subtract the mean from each channel and then divided by the standard deviation. So that means we want to, recenter each image to 0, and with a variation equals 1. So that's what we want to do with this one. So, but where do the mean and the variance come from? We need to find them. So this is how we do it. First, we get the normalization layer. You see layer 0, 1. Layer 0. That's the first one, because we in Python we use a zero-based indexing. So we call adapt and give the data which X string, which means we ask the normalization layer to use our training data to calculate a mean and the variance to be used later on, for normalization. All right. So after that, we're gonna define our encoder model. I also call it a feature extractor. Either way, okay. So basically, you can see here, we load in the ResNet 50 model with the head cut off, with the top layer removed. And also we say weight equals none, means we do not want to use a pre-trained model. We just use the architecture itself, okay? And also we change the input shape. So once we have the architecture of the ResNet ready, we first create an input layer, and then the input, we pass the input into our data augmentation that we defined here to either randomly rotate or flip, and also do the normalization as well. We got augmented samples. And after that, we pass those augmented samples into our ResNet. We just, load it in. And the output from our ResNet is the final output. So then we have inputs, outputs. We create a Keras model, take the input and output. The name is optional, so we return the model. So that's how we create the encoder. So we can create the encoder and see a summary. And if you want to see, I can have a quick look. We can have a quick look at it. So this is the quick input layer, and this is the data augmentation, and finally the ResNet 50. So that's this structure. Let's go back. Okay, we are here. Next, we define some, hyperparameters like a learning rate, batch size, so on and so forth. And I'm going to mention this one, the hidden units. Like I mentioned earlier, we don't want to, from the 2048 right jump to reduce to 10. We need a middle ground. So this one we call a hidden layer, and its output is we defined here is 512. So that's a middle ground from 2000 something to 500 something to 10. So that's something here. Okay, so that's the 550. And secondly, above these project units, that's the dense layer that when we train the base model in the contrastive way. And the rest of it is the same thing. Temperature is something that used to control the loss function that I will explain later. Okay, so we have those hyperparameters defined. Now let's define a function to create the classification model. Here we have two parameters. The encoder that we create use this function, and the second one is whether or not the model is trainable. I mean the encoder, the base model is trainable. By default, is true. Okay, so let's see how we do it. So first of all, we go through every layer in the encoder to assign them to set up the trainability that we defined. We pass in as a second argument. And for the neural network, first the input layer, and the input, then we pass it into the encoder, get the feature. Then the feature, we go through dropout, dense, dropout, dense. Pay attention to the last dense layer. The activation function, we use softmax, which give us the output like probability, okay? Once we have that ready, just like before, we have an input and output. We just create a Keras model in such a way. And this is our classifier neural network model. So we compile them, specify the learning rate, the loss, and also the metrics we are going to use and the return. All right. So once we at this point, we are ready to conduct our first experiment. And in the first experiment, we are gonna create the neural net and train it in the traditional way. So what we did, first we create an encoder, which is the base of the neural network. Then we add a layer, which the 4 layers, basically 2 of them are dense layers. So we call this one. Please note that we didn't pass the second, we didn't give the second argument. By default, it is trainable. So this is our purpose to train the base model. So that's correct. And summarize, and then we use one call feed to train it by passing the training data and the number of epochs and batch size it will train. I think here we give 50 epochs. And after training, we run it all over our test data, and it will return 2 things. The first one is loss. The second one is accuracy. So we take the second one as accuracy and print it out. So that's our experiment. The second experiment is to use our supervised contrastive learning. With the knowledge before, it's much easier. But before we start, we need to define our new loss function. The loss function will use the temperature to control the calculation. Let's see here, this is how it works. when we do the loss function calculation, it needs two things. One is the samples labels, the labels of the samples. The second is the features that generated by from those batch samples. So first thing, we normalize those vectors. We got normalized vectors. Once we have normalized vectors, we transpose it and use matrix multiplication. So here, the normalized feature vectors are, are matrix shape. It has batch size as row numbers, the number of rows, and the column size is the length of the vector. So when we do the transpose, we do the calculation, do the multiplication, we got batch size by batch size matrix. And lastly, we divided such a matrix element-wise by the temperature. It's like some kind of a control the value. Finally, we call our convenient function from TensorFlow add-on, and to do the calculation that measure the similarity. Okay. All right. So one more thing that we need to do is we need to define a convenient function to just add one layer to our encoder. Pretty much the same thing. We have the encoder, and after the encoder, we just add a dense layer. The output number is project units. I think it's 100 or 200 something there defined above. Okay, so finally we group them together. So that's how it works. All right. So now we to train in the second experiment to train the the neural network in the contrastive learning way. We need to train it in two steps. The first one is to train the base model or the encoder. So we create the encoder. We add the just one layer, dense layer to the head, and then we we compile it. But here, pay attention. The loss function, we use what we have just defined above that can compare the output, which are features instead of classifications. So we can use our own loss function just defined above. Then summary, and then we train it. And then finish the training. Once we finish the training, we keep the base model unchanged, but now we add 4 layers. 2 of them are drop out, the 2 others are dense, as we show above. The same thing, but this time we keep the base model frozen. That means we don't want to train the base model. We only want to train the newly added layers. So after that, we just train it. So basically, once we use this create a classifier, this classifier neural network has exactly the same structure as what we do in the first experiment. In the first experiment here, exactly the same. Okay, Just we freeze the base model when we train the second classifier. Okay, so we do the same thing, do the feed to train, and after the 50 epochs, we check. We run the evaluation over the test data to see how our model works, and we got our result. All right, that's the original, original code of the. I already run it. The difference between the two experiments are not very big. I think one we got like 77% accuracy, and with the constructive learning we got 80 or 81. So that means we got like a 3 or 4% of improvement. Not very big, like I mentioned before. Contrastive learning by itself is not powerful enough, but to get a better result, you have to combine it with other learning technologies. All right, but I find that we can improve this learning technology by a few things. First of all, we can do fine-tuning after we completed the constructive learning, which is phase 3 training. So, which means we unfreeze the base model and then train the last phase in the last phase. So everything can be retuned. Secondly, I found the structure of ResNet 50 is not good for Sci-Fi 10. The reason is that you see the structure here. We have convolution, a lot of convolution layers. If because this architecture is designed for ImageNet data set, but once we use for Sci-Fi 10, because the image size greatly reduced, here we have a 32 by 32. After a few convolutional layers, especially the last block, the feature map becomes instead of it's become a 1 by 1 image, size 1 by 1. Although the channel is quite big, like 500 or something, but it's become 1 by 1, and by 1 by 1, then those 3 by 3 kernels doesn't cannot exhibit its full power, so it's useless in my opinion. So that's why we can cut off the last block or even the last 2 blocks, probably make it better. I already did some experiment, and I'm gonna show them below, but let me to see some other improvement that we can do. Okay. Secondly, I think we can get a better result if we combine with transfer learning. When we load the ResNet dataset, ResNet architecture, we do not load the weight. That means we do not use the pre-trained model. But imagine if we do use a pre-trained model, for example, trained with ImageNet dataset, then the base model already has a lot of useful information, which can be, greatly improve our work. So I haven't tried that, but I think that's a good direction to try. But today I'm gonna show some other things that I have done. you see I have two versions. In addition to the original version, let's take a look of the first one. If I do see the difference, the difference is in the beginning, which is not very large. First of all, I'm gonna evaluate each after each epoch. So instead of and I also add some plotting. I will show the plotting, and I changed the data augmentation a little bit. The previous one, you see, you change the width and height randomly, but sometimes I vary if it becomes bigger than 32 by 32, what will happen? I'm not so sure. So here, what I do is I comment out the random width and height. Instead, I'm introduce a random translation. And also I changed a little bit the parameter. Instead of 5% of 2% of the 360 degree, I use 5%. And also I increase the batch size. I find the training is not very stable. And also I do a fine tuning 20 epochs, and that's it. So that's pretty much it. So let's see some plotting from my so this is experiment 1 that I trained the neural network in the traditional way. You see that I got the test set here. I think that the best I got is 70 something, 77 or 76. But you see these spikes pointing down. That's not a good sign. So that means either something wrong with the structure or something not so stable. And let's see what we do in the second experiment. Let's first look at the loss function, which is phase 1. We train the base model to produce more discriminative feature vectors. We see they're quite good, and then we see the fine-tuning part of after the constructive learning. For the training data, the accuracy is constantly going up, but for the test data, you see it's almost doesn't get too much improvement. So that explains the base model has already provided the majority of the discrimination power. So you couldn't get too much out of it, because most of the job has done in the phase 1 base model training. That produce a very meaningful or feature vectors. That's the point of contrastive learning. And in the second experiment, let's see div. Okay. You can see that I instead of from the output of the ResNet, I actually cut off from the middle, from the last from the second block from the bottom. I actually, if you take a look of its call for block 6. So let's take a look of it. So I take the output from here. So the last block I just removed. I just take the output from here and then connect it with the rest of layers that I added on. Okay. So let's go back here. Nothing else. So the same thing as before, and I just train it. So here, this time, I get slightly better result. 1. You see the spike is smaller than before. So that means without the last block of convolutional layers, the neural network get more stable. And the accuracy, we didn't sacrifice accuracies, even though we remove the last block of convolution layer. And secondly, let's see the loss function. You see this a little bit smoother than before, than the one before, and the last one, the accuracy. Yeah, so pretty much the same thing as before, not significant. But if we do want to check, you can see I run my 2 versions, 2 improved versions, and I got these 2 output. So we can quickly, take the test accuracy. I think I should do this. Test accuracy from our, I only have 2 output file. So in the first, in the first experiment, which I use the whole base model, I got experiment 1 training in the traditional way, I got 78. And our contrastive learning got close to 83. In the second version, instead of use the whole ResNet 50 as base model, I removed the last block and use probably like 3/4 of the neural network as the base model. And you can see the accuracy get better than before in both the experiment, So that's the my experiment. I will post the source code for you to try. The link I will post in the YouTube channel once this video is already uploaded to our youtube.sharknet.ca. Yeah, so you can feel free to try. Yeah, so this is the introduction of a new technology. Hope it will help you to in your future work. Thank you very much.